Somewhere beneath the rugged terrain of the Andes, the deserts of Nevada, or the highlands of Australia, the Earth holds one of its most timeless treasures, silver. For thousands of years, this gleaming metal has been mined, traded, and cherished. But today, silver is no longer just a symbol of wealth or ornamentation. It powers smartphones, solar panels, and even satellites. And to meet this modern demand, the silver mining industry has evolved into a sophisticated and highly technical global operation. But what does it actually take to extract millions of ounces of silver from the Earth each year? The answer is a fascinating blend of geology, engineering, chemistry, and brute industrial power. In this episode, we're going deep into the world of silver mining, from exploration to smelting and everything in between. Long before modern machinery and high-tech refining methods, silver captivated civilizations across the globe. Its shimmer adorned the crowns of kings and the coins of empires. The story of silver mining stretches back over 5,000 years, beginning in ancient Anatolia, modern-day Turkey, where early miners used stone tools to chip silver ore from cave walls. By 500 BCE, the Greeks were extracting silver on a grand scale from the laurium mines near Athens. That silver helped fund the Athenian navy, and in many ways, fueled the rise of democracy. Meanwhile, in the Americas, indigenous cultures like the Incas revered silver as a sacred metal, calling it the tears of the moon. Everything changed in the 16th century, when the Spanish conquest of the New World unlocked vast silver deposits in Potosi, in present-day Bolivia. At its peak, this one mountain produced so much silver that it funded half of Europe's economy. But that wealth came at a brutal cost. Millions of indigenous and African slave laborers toiled under horrific conditions to meet colonial demand. As centuries passed, silver mining spread across continents, from the Comstock lode in Nevada during the American Wild West to high-tech operations in Australia, Canada, and China today. Each era brought new tools, new challenges, and new understandings of both silver's value and its consequences. What hasn't changed is our fascination. Silver is more than a metal. It's a mirror reflecting human ambition, ingenuity, and at times exploitation. And as we explore how silver is mined in the modern era, we carry the weight of that legacy with us. The journey begins long before a single rock is moved. It starts with exploration, weeks, months, and sometimes years of geologists combing through remote mountain ranges and deserts in search of silver-rich deposits. Using a combination of geological surveys, satellite imaging, and exploratory drilling, they search for the telltale signs of mineral veins hidden deep underground. Once a promising site is found and test samples confirm sufficient silver content, a mining plan is drawn up. Environmental permits are secured, infrastructure is developed, and massive equipment begins to move in. Now, it's time to dig. Depending on how deep the silver deposit lies, mining operations take one of two routes. If the silver is close to the surface, open-pit mining is the method of choice. This involves stripping away layers of earth, known as overburden, to reveal the ore beneath. Massive shovels and dump trucks haul out thousands of tons of rock each day, carving a giant staircase-like pit into the ground. If the deposit lies deeper underground, things get more complex. Vertical shafts are drilled straight down, and horizontal tunnels are carved through solid rock. Workers navigate a maze of passageways, often more than a mile beneath the surface, using drills and explosives to break apart ore. Whether surface or underground, the goal remains the same: bring silver-bearing rock to the surface as efficiently as possible. At this stage, the ore still looks like nothing more than ordinary rock. In fact, each ton of raw material might contain just a few grams of silver. To get to the metal locked inside, the ore is trucked to a processing facility, where it undergoes a powerful mechanical transformation. process starts with crushing. Giant jaw crushers bite down on the rocks, reducing them to chunks the size of baseballs. Those fragments then pass through secondary crushers, getting smaller and smaller until they resemble gravel. But to truly release the silver, the material needs to be pulverized. That happens inside large rotating mills filled with steel balls. As the mill spins, the ore is ground into a fine gray powder, similar in texture to flour. Only now is the silver ready to be separated chemically from the waste. With the ore reduced to powder, it's time for science to take over. The method used depends on the type of rock and how the silver is embedded. If the silver is found in sulfide minerals like galena or chalcopyrite, the ore goes through a process called froth flotation. In large tanks, the powdered ore is mixed with water, air bubbles, and a cocktail of chemical reagents. As the mixture churns, silver-containing particles attach to the air bubbles and rise to the surface, forming a foamy layer that can be skimmed off. What's left behind is mostly waste. If the silver is embedded in oxidized rock, a different technique is used, cyanide leaching. Though controversial, this method is highly effective. The ore is soaked in a weak cyanide solution, which dissolves the silver into a liquid form. That solution is then filtered, and the dissolved silver is extracted using zinc or activated carbon. Whichever method is used, the result is a concentrated form of silver. Still not pure, but now in high enough quantities to be economically viable. With the concentrate in hand, the next step is smelting, an ancient process brought into the modern age. The concentrate is shipped to a specialized facility where it's heated in furnaces that can reach temperatures well over 2000 degrees Fahrenheit. At these extremes, the silver melts and begins to separate from the impurities. Fluxes like silica or lime are added to help the process. They bind to unwanted materials, which float to the top as a thick layer of slag. The heavier silver sinks to the bottom, forming a molten pool of metal that is then poured into molds. As it cools, the silver solidifies into rough ingots, still containing traces of other metals like copper or lead. To reach the high purity levels needed for commercial use, the silver must undergo one final critical stage: refining. Refining begins with electrolysis. The rough silver ingots become anodes, electrodes that dissolve when electric current is applied. They're suspended in a tank of silver nitrate solution, alongside thin sheets of pure silver, which act as cathodes. As electricity flows, silver atoms from the impure anodes dissolve into the solution and redeposit themselves onto the cathodes in pure form. Over the course of several days, these cathodes grow into thick, gleaming sheets of high-purity silver. Meanwhile, any impurities either fall to the bottom of the tank as sludge or remain suspended in the liquid. The refined silver is then melted once more and poured into standard bars, each one stamped with its weight, purity, and a unique serial number. Some of these bars are headed to bullion vaults and investors. Others are destined for industrial plants, where they'll be turned into wires, mirrors, circuits, and connectors. Once refined, silver enters the global economy through a complex and high-security supply chain. Each bar is carefully weighed, tested, and sealed in tamper-proof packaging. From there, they're shipped to precious metal exchanges, manufacturers, and refineries around the world, often under armed guard or with GPS tracking. The applications are nearly endless. In smartphones, silver conducts electricity with unmatched efficiency. In solar panels, it converts sunlight into clean energy. In hospitals, it acts as an antibacterial coating. And in jewelry, it dazzles and endures. Every ounce of silver may look the same to the naked eye, but the journey behind each bar spans continents, cultures, and centuries of human progress. Silver isn't just a precious metal, it's a story of discovery, transformation, and relentless ingenuity. And now, you know how millions of ounces of it are mined, processed, and put to use, one shimmering bar at a time. Thanks for watching. If you love learning how everyday materials are made, from the mines to the machines, hit that subscribe button and join our growing community. We've got more incredible journeys coming your way, from the heart of the earth to the hands of innovation. From the smartphones in our pockets, to the wiring that keeps our homes bright, and even the engines that drive our cars forward, copper is everywhere. It is one of the most essential metals on Earth, and yet, very few people know exactly how it's pulled from deep within the ground and turned into shiny, pure copper that powers our modern world. Thousands of meters below the Earth's surface lies a vast treasure chest of copper ore. But unlocking that treasure isn't as simple as digging with a shovel. It's a process that requires giant machines, explosive force, precision chemistry, and weeks, sometimes months of transformation before a rock can become one of the world's most useful metals. Today we're taking you inside that journey. From exploration and blasting, to crushing, smelting, and refining, this is the mind-blowing story of how copper is mined, processed, and made ready for the world. But before we dive in, don't forget to hit subscribe, tap the notification bell, and give this video a thumbs up. Trust me, you don't want to miss what's coming next. Copper is often called man's first metal. Why? Because it was one of the very first metals ever used by humans, dating back more than 10,000 years. Ancient civilizations like the Egyptians and Mesopotamians discovered that copper wasn't just shiny and beautiful, it was also strong, malleable, and resistant to corrosion. That meant it could be shaped into tools, weapons, jewelry, and even the very first plumbing pipes. Fast forward thousands of years, and copper remains just as important, if not more. Today, copper is the backbone of modern technology. It conducts electricity better than almost any other common metal, making it essential for power lines, motors, electronics, and renewable energy systems like wind turbines and solar panels. Without copper, much of the modern world would literally go dark. In fact, copper demand is skyrocketing. With electric vehicles, green energy, and global electrification, the world now consumes over 20 million tons of copper every single year. And where does all that copper come from? Not from recycling alone, though recycling is hugely important, but mostly from mining deep deposits hidden inside the earth. These deposits aren't pure copper metal. Instead, they're ores, rocks that contain copper minerals like chalcopyrite, bornite, and malachite. Typically, copper ores only contain a small percentage of actual copper, often less than 1%. That means for every ton of copper extracted, miners must move and process hundreds of tons of rock. This is where the journey begins. Locating those deposits, digging massive mines, and then transforming ordinary rock into one of the most valuable metals on Earth. So, how do we actually find copper in the first place? The Earth's crust contains copper scattered almost everywhere, but only certain locations have concentrations high enough to be mined profitably. That's where exploration geology comes in. Geologists begin by surveying landscapes using satellite imagery, mapping rock formations, and analyzing soil chemistry. They look for signs of copper minerals on the surface, greenish stains of malachite, or bluish hints of azurite. But since the richest deposits often lie deep underground, scientists rely on advanced tools like magnetic surveys, seismic studies, and drilling core samples. When drilling, a cylindrical piece of rock is pulled out of the ground, often hundreds of meters deep. Geologists examine these cores to estimate the size, depth, and grade of a copper deposit. If the results are promising, companies spend years and millions of dollars conducting feasibility studies. They ask questions like, how much copper is really here? How much rock must be moved? What's the environmental impact? Can this mine be profitable for decades? Once approved, it's time to dig. And depending on the deposit, miners use two main methods: open pit mining and underground mining. The journey starts at the primary crusher. Here, gigantic rocks, sometimes the size of a refrigerator, are dumped into a machine with steel jaws. These jaws slam together with immense force, reducing boulders into fist-sized chunks. The process doesn't stop there. Secondary and tertiary crushers further reduce the pieces down to gravel-like sizes. Why so small? Because the smaller the particles, the easier it is to free copper minerals from the surrounding rock. After crushing, the ore heads to the grinding mills. Imagine enormous drums, each bigger than a bus, rotating day and night. Inside, steel balls or rods tumble with the crushed ore. As the drum spins, the heavy balls crush the ore into a fine powder. At this stage, it looks less like rock and more like wet sand or even muddy slurry. This fine grinding is crucial because copper minerals are often locked within the tiniest grains of rock. Now comes the ingenious part: separating valuable copper minerals from waste rock. Since copper minerals often have unique surface properties, miners use a method called froth flotation. This step is magical when you think about it. Out of tons of dull gray rock, we've now isolated a small but powerful concentrate brimming with copper minerals. But we're not done yet. The concentrate still contains sulfur and other impurities, so it needs to be transformed into pure, usable metal. At this stage, enormous conveyor belts and pipelines move the copper concentrate to smelters or processing plants. From muddy slurry, the journey is about to leap into the world of fire, heat, and chemistry. After concentration, the copper-rich slurry, now upgraded to about 30% copper, travels to one of the most dramatic stages in metallurgy: smelting and refining. This is where chemistry, heat, and human ingenuity combine to transform dull concentrate into glowing, usable copper metal. The concentrate, still containing sulfur and iron, is dried and fed into huge furnaces. Imagine steel chambers large enough to hold a small house, burning at over 1200 degrees Celsius to 200 degrees Fahrenheit. The molten matte is then transferred to another furnace called a converter. Here, air or pure oxygen is blasted through the molten material. The oxygen reacts with the remaining sulfur and iron, driving them out as gas or slag. The result, a product called blister copper, so named because its surface appears blistered with bubbles of escaping gas. This blister copper is about 98 to 99% pure. But 98% isn't good enough for modern technology. Smartphones, electrical wiring, and medical devices demand ultra-pure copper, 99.99% purity. To reach this perfection, blister copper undergoes electrolytic refining. When the process is complete, what emerges are sheets of copper so pure they gleam like mirrors, ready to be rolled, drawn, and manufactured into countless applications. From ore dug deep in the earth, we've now produced one of the world's most essential materials. The copper you see in wires, plumbing, cars, electronics, even renewable energy systems like wind turbines and solar panels, all trace their origins back to this fiery transformation in smelters and refineries. If you've enjoyed this journey into the hidden world beneath our feet, imagine how many more stories the Earth is waiting to tell us. Subscribe to the channel, hit that notification bell, and join me as we uncover more secrets of science, nature, and the incredible materials that shape our modern life. Don't just watch, be part of the adventure. Have you ever held a sapphire in your hand? That brilliant blue stone sparkling under the light isn't just a gem, it's the product of millions of years of nature's work and decades of human effort. Today we're taking you deep inside the world of supergiant sapphire mining, from rugged mountains in Montana to cutting-edge processing facilities, to see how one of the world's most valuable gems is found, extracted, and transformed into treasures that last for generations. Before we dive in, don't forget to like, subscribe, and hit that notification bell for more fascinating behind-the-scenes journeys of how the world's most valuable materials are made. Sapphires aren't just beautiful stones, they're a type of corundum, a mineral made of aluminum oxide, and they rank 9 out of 10 on the Mohs hardness scale, just under diamonds. What makes sapphires special is their trace elements. Tiny amounts of iron and titanium give them that deep, royal blue color. Other trace elements can make them pink, green, yellow, or even colorless. In the US, the most famous sapphires come from Montana, a state often called the Treasure State. Here, sapphires were first discovered in the 1860s by gold miners. They weren't looking for gemstones, they stumbled upon them while panning for gold. But soon, sapphire fever spread. By the late 19th century, the famous Yogo Gulch deposit was discovered. Yogo sapphires are legendary, prized for their uniform cornflower blue color, exceptional clarity, and the fact that they don't need heat treatment to enhance their beauty. From royal crowns in Europe to engagement rings in the US, sapphires have always carried an air of mystery, wealth, and prestige. Imagine standing in the wide-open landscapes of Montana. Rolling hills, gravel bars along the Missouri River, and rugged gulches carved by ancient glaciers. This is sapphire country. Sapphires are typically found in placer deposits, where ancient rivers carried them down from eroded mountain rocks. Over time, the heavier sapphires settled in gravel beds waiting to be discovered. To locate sapphire-rich areas, geologists study the land, analyzing sediment layers and rock formations. In modern mining operations, giant excavators and dredging machines are used to scoop up tons of gravel and sediment. Every shovelful could contain sapphires, but the odds are small. On average, miners might move hundreds of tons of rock to find just a handful of quality gems. That's what makes sapphire mining both a gamble and a wonder. Now let's head inside a supergiant mining plant. Massive bulldozers dig up sapphire-bearing gravel, sometimes working through layers that are millions of years old. The raw gravel is loaded into washing plants. High-powered water jets separate lighter material from heavier stones. Sapphires, being heavier, settle at the bottom along with other dense minerals. Workers and machines sift through the concentrate, looking for flashes of blue, green, or yellow, the telltale sparkle of a sapphire. The excitement of finding a sapphire hasn't changed much since the gold rush days. Each discovery feels like unearthing a hidden star from the earth. A rough sapphire doesn't look like the sparkling gemstone you see in jewelry stores. It's often cloudy, irregular, and dull. Here's how it's transformed. Grading. Experts examine the rough stone for color, clarity, and size. Cutting. Skilled lapidaries use diamond-tipped saws and precision machines to cut the stone. The goal: maximize brilliance while minimizing weight loss. Polishing. Facets are polished to perfection, unlocking the sapphire's fire and sparkle. Heat treatment. Optional. Some sapphires undergo controlled heating to enhance their color. But remember, Yogo sapphires from Montana are naturally beautiful and rarely need treatment. The result? A gemstone that can fetch anywhere from a few hundred to tens of thousands of dollars per carat. While sapphires are famous in jewelry, did you know they also power modern technology? Industrial sapphire glass. Scratch-resistant, used in watch faces, smartphone screens, and scientific instruments. Laser technology. Sapphire crystals doped with titanium create powerful blue lasers. Electronics. Thin sapphire wafers are used in semiconductors and LED manufacturing, so sapphires aren't just about beauty. They're also about science and progress. Behind every sapphire is a story of people. In Montana, mining towns grew around sapphire deposits. Families worked the gravel bars together, passing down stories of luck and discovery. Lapidaries, the skilled craftsmen who cut and polish gems, dedicate years to mastering their art, turning rough stones into dazzling treasures. Jewelers and designers then carry the final product to customers around the world, where sapphires symbolize love, loyalty, and wisdom. Mining also brings challenges, balancing economic opportunity with environmental responsibility. Modern operations focus on land restoration, water recycling, and sustainable practices to protect Montana's natural beauty. Think about this. A sapphire you might see in a ring today could have formed over 500 million years ago, deep within the Earth's crust. From its birth under extreme heat and pressure, to its discovery in a Montana gravel bed, to its transformation in a cutting workshop, that journey is nothing short of extraordinary. Thanks for watching, and until next time, keep discovering. Beneath the Earth's crust, hidden in ancient volcanic formations, lie some of the most prized treasures known to mankind. Diamonds. For centuries, these shimmering stones have captivated royalty, industries, and investors alike. But their story begins long before they ever reach a jeweler's display. The history of diamond mining stretches back over 2,500 years to ancient India, the first known source of diamonds. These early gems were found in riverbeds and traded along the Silk Road, believed to bring strength, invincibility, and spiritual clarity. By the 18th century, Brazil had become the world's largest supplier, before the discovery of massive deposits in South Africa changed everything. In 1867, a young boy found a shiny stone along the Orange River, a 21-carat diamond that sparked a modern diamond rush. This led to the founding of some of the world's most famous mines, including Kimberley, home to the legendary Big Hole. Today, diamond mining is a high-tech global enterprise. The world's largest mines span across continents, from Jwaneng in Orapa in Botswana, to Mirny in Russia, Venetia in South Africa, and Diavik in Canada. Some operations reach depths of over 1,000 meters, and each year, more than 130 million carats of rough diamonds are produced globally. But how are these tiny crystals of carbon extracted from solid rock? And what does it take to bring them from the Earth's core to the world's most exclusive boutiques? Join us as we journey deep into the heart of modern diamond mining, a world of massive machines, precision science, and sparkling ambition. Geologists use satellite imaging, geophysical surveys, and soil sampling to identify promising sites. Once a potential kimberlite deposit is located, it's drilled and sampled to assess the concentration of diamonds. This process can take years and millions of dollars in investment before a mine is approved. Only a small percentage of kimberlite pipes actually contain diamonds in commercially viable quantities. If one does, the project moves into the development phase. In open-pit operations, huge amounts of overburden, layers of soil and rock, must be removed. The process begins with explosives, followed by massive hydraulic shovels and dump trucks that can carry up to 400 tons of rock at a time. This material is hauled to the primary crushing stations, where the hard kimberlite rock is broken down to manageable sizes for further processing. Once the ore is brought to the surface, it enters the primary crushing phase. Here, giant jaw crushers reduce large rocks into smaller pieces. The material is then passed through secondary and tertiary crushers to reduce it even further. By now, it resembles gravel-sized particles. The goal? To liberate the diamonds trapped within the rock matrix. From here, the crushed ore is sent into a washing and screening circuit to separate fine particles and slurries. These finer materials are essential because diamonds are often only a few millimeters in size. Next, the slurry moves through dense media separation tanks, where materials are separated based on their density. Since diamonds are extremely dense, they sink to the bottom, while lighter waste material floats. The diamond-bearing concentrate is now ready for recovery, but finding these tiny gems in tons of rock still requires a highly specialized process. Now, the real treasure hunt begins. the diamond-rich concentrate is fed into X-ray fluorescence machines which detect the unique light refraction of diamonds. When a diamond is identified, a jet of compressed air precisely ejects it from the conveyor belt into a separate container. This method is remarkably effective, recovering over 98% of diamonds in a single pass. Recovered diamonds are still raw and coated in grime. They undergo acid cleaning to remove any residue from surrounding rock. At this stage, they're referred to as rough diamonds. Next, the diamonds are hand-sorted into various categories based on size, shape, color, and clarity. This step is done by trained gemologists who evaluate thousands of stones each day. Industrial-grade diamonds used in tools and cutting equipment are separated from gem-quality diamonds, which move on to valuation and certification. A single mine can produce up to 10 million carats annually, but less than 25% will be suitable for jewelry. The rest are used in lasers, drills, and grinding equipment. Every diamond is registered, tagged, and documented for traceability, ensuring ethical sourcing and conflict-free certification, a process now mandated by the Kimberlite process. Once sorted and certified, rough diamonds are packed in secure, tamper-proof containers. These are shipped to international trading hubs like Antwerp, Dubai, or Mumbai, where they enter the global market. Auction houses and diamond companies bid on lots worth tens of millions of dollars. Once sold, the diamonds are sent to cutting and polishing centers in India, Israel, or Belgium. There, artisans use lasers and high-speed rotary tools to cut each stone with mathematical precision, maximizing brilliance and carat weight. A rough diamond may be cut into one or several polished stones, depending on the original size and quality. Each cut is planned in 3D software before any physical shaping begins. Finally, the polished diamonds are graded by labs such as GIA or IGI, receiving their official certification that includes the famous 4 C's: cut, color, clarity, and carat. From mine to market, the journey of a diamond can take months, sometimes years. But every sparkle begins with one thing: rock moved, sorted, and refined through one of the most sophisticated mining operations on Earth. More than just sparkling gemstones, diamonds represent a fusion of Earth's deepest secrets and human ingenuity. From volcanic pipes to laser-guided polishers, their path is paved with geology, engineering, and skilled craftsmanship. But today's diamond industry is also increasingly focused on responsibility, minimizing environmental impact, ensuring fair labor practices, and building transparency through blockchain and digital tracking. Massive diamond mines employ tens of thousands of people and contribute billions to local and national economies. Yet, each carat extracted also comes with a responsibility to protect the land, the people, and the legacy these gems will carry into future generations. The next time you see a diamond glint under the light, remember, it's not just a symbol of love or luxury. It's the result of science, technology, global effort, and a journey that spans millions of years beneath our feet. Have you ever wondered how nature's hardest rocks are cut, shaped, and transformed into tools, buildings, and even industrial machines? Today, we're taking you inside a supergiant cutting rock plant, where enormous slabs of basalt are mined, sliced, and crafted into something truly extraordinary: the basalt mill, a tool that has powered grinding, milling, and stonework for centuries. Before we dive in, make sure to hit that like button, subscribe, and tap the bell icon so you never miss more behind-the-scenes stories of how the world's most essential materials are made. Basalt isn't just any stone. It's one of the most common rocks on Earth, born millions of years ago from volcanic eruptions. When molten lava cooled rapidly, it hardened into basalt, a rock so tough it's been used for everything from ancient roads to modern skyscrapers. In fact, the Romans built some of their most enduring roads out of basalt, and many of those stones still exist today, nearly 2,000 years later. That durability is why industries still love basalt. It's hard, dense and resistant to wear, perfect for making mills that grind grain, crush rock, or process materials in factories. Imagine standing next to a single block of basalt the size of a school bus. That's what workers here deal with every single day. The first step in the process is quarrying. Using diamond-tipped wire saws, hydraulic drills, and sometimes even controlled explosives, workers cut enormous chunks of basalt free from the quarry walls. The diamond wire saw works like a giant cheese slicer, slowly grinding through solid rock. It's strong enough to cut through basalt, a rock that's harder than steel in some cases. Once freed, these massive blocks are hauled out of the quarry by colossal wheel loaders and trucks. Each block can weigh tens of tons, requiring special equipment just to move. But these raw blocks are only the beginning. The real magic happens inside the cutting plant. The sound hits you first. The roar of saws, the hiss of water cooling blades, and the deep hum of conveyors. This is where basalt is tamed. The giant blocks are placed onto conveyor beds, where massive gang saws slice them into manageable slabs. These saws use blades lined with industrial diamonds, kept cool with constant streams of water. Without water, the heat and friction would destroy the blades in minutes. Once slabs are cut, they're moved to CNC, computer numerical control machines. These robotic arms can cut, polish, and drill the basalt with incredible precision. Whether the goal is a smooth countertop, a floor tile, or the circular shape of a millstone, CNC machines ensure accuracy down to the millimeter. Here, slabs are polished to reveal basalt's natural beauty, a dark, almost metallic sheen with tiny sparkling crystals inside. Some slabs are left rough, perfect for industrial uses. Others are ground smooth for decorative and architectural projects. Now comes the highlight, transforming raw basalt into a mill. First, workers select a high-quality slab with no cracks or impurities. Then, massive circular saws cut out the round shape. The stone is gradually honed into a perfectly flat disc. Grooves are etched into the stone's surface, carefully designed patterns that help grind grains or crush materials efficiently. These grooves are more than just decoration. They control how food moves across the millstone. Finally, the basalt mill is mounted onto a spindle or frame, ready for use in everything from traditional flour mills to modern industrial grinders. It's fascinating, a piece of volcanic rock, formed by fire thousands of years ago, now shaped by human hands into a tool that feeds millions. But basalt doesn't stop at mills. In this plant, basalt is cut into tiles, pavers, countertops, and even fibers. Yes, basalt can be melted and spun into thin fibers, creating a material that's stronger than steel yet lighter than aluminum. It's even being used in aerospace and construction industries. You might wonder, can stone be recycled? The answer is yes. Scraps and offcuts from basalt cutting are crushed into gravel or ground into powder. These byproducts are used in road construction, cement manufacturing, or even as mineral supplements in soil. Nothing goes to waste in this process. And because basalt is natural, non-toxic, and incredibly durable, it remains one of the most eco-friendly building materials on Earth. Behind every machine are people. Skilled workers who understand basalt's quirks, where it might crack, how to cut it safely, and how to polish it just right. For many workers here, basalt isn't just a job, it's tradition. In some regions, stone cutting has been passed down for generations. Families who once shaped millstones by hand now operate high-tech machinery. But the pride is the same. Take a moment and think. When you enjoy a slice of bread, step on a tiled floor, or drive down a highway, you may be experiencing the results of basalt. It's not just rock, it's a silent partner in civilization. From the dawn of farming to the rise of modern cities, basalt has been there, providing the strength, durability, and resilience we rely on. It's one of the toughest stones on Earth, yet humans have found ways to shape it, use it, and depend on it for thousands of years. And here inside this supergiant cutting rock plant, that story continues, where raw stone meets human ingenuity, and nature's toughest material is transformed into tools that keep our world turning. If you enjoyed this journey, don't forget to like, subscribe, and hit the bell icon to explore more amazing behind-the-scenes stories of how the world's essential materials are made.